The difference between a strong acid and a weak acid is based on the extent of the proton transfer between the acid. This formula here, HA, is just the general form for an acid, and water. A strong acid is going to almost completely donate its proton to the water, meaning that the reaction would shift towards the right and go towards completion. A weak acid, on the other hand, doesn't donate its proton as readily, so instead it's going to establish an equilibrium, such as the one shown here. One other thing to note, if we look at acid-base pairs, so HA is our acid, water is acting as our base. That means the hydronium is our conjugate acid, and A- is our conjugate base. If we have a strong acid, then its conjugate base is actually quite weak. If we have a weak acid, that means that the conjugate base is strong. This table here then shows you some of the relative strengths of some common Bronsted-Lowry acids and bases. And you can see as acid strength increases, something like perchloric acid is a very, very, very strong acid. Its conjugate base is very, very weak. So this side, increasing conjugate base strength, goes down. Something like ammonia is actually a very, very, very weak acid. So the amide ion is a very, very strong base. Some examples of strong and weak acids. Really, there are only 5 strong acids known. Any other acid is weak. HCl, hydrochloric acid, hydrobromic acid, sulfuric acid, nitric acid, and phosphoric acid. Actually, we've forgotten one here. There's also perchloric acid, which is HClO4. These ones are all strong acids. Any other acid is weak. Those include carboxylic acids, things like hydrofluoric acid, carbonic acid, hydrosulfuric acid, boric acid. There are more examples than this, but if it is not one of these strong acids listed on this side here, then you can safely assume that it's a weak acid. There are a couple of other definitions we need to talk about for acids, and they are based on how many protons they have that could possibly be donated to a base. Monoprotic acids, mono meaning one, means that it contains only one proton that is able to be donated. Some examples would be HCl, HBr, HNO3. Diprotic acids, di meaning two, means that the acid has 2 possible protons that can be donated to a base. Something like H2SO4 can donate both of its protons to a base. Triprotic acids then have 3 protons that could be donated to a base. Something like phosphoric acid is a triprotic acid. For bases, it's pretty similar. We're going to set up the general equation of B- plus water, B- being our base, reacting to give a BH plus OH minus. If we have a strong base, it will accept a proton from water very readily, and this reaction, again, will almost go to completion. If we have a base that is a weak base, it is not going to easily accept that proton from water, and an equilibrium will be established. Again, if we have a strong base, then we're going to have a weak conjugate acid. If we have a weak base, then we have a strong conjugate acid. Examples of strong bases: any of the hydroxides from group 1 elements as well as group 2 elements are strong bases. The difference being these ones are soluble, whereas these ones are insoluble. Pretty much all other bases are going to be weak bases. A few examples would be ammonia, sodium phosphate, as well as all the organic bases, things like urea, methylamine, things that contain nitrogen.